So now we begin the acids bases chapter, and we learned a little bit about acids and bases. So every once in a while you'll see review here, and that's actually I'm going over material from previous chapters, but I thought it would be good to cover it anyways in a way for reviewing for your final exam, but also to give you a point of reference so you can go back to your earlier notes or earlier sections in the text and look for information. So properties of acids. So one of the first properties they always say about acids, and one of the first things we also tell you not to do, is not to taste chemicals. But acids are sour and bases are bitter. Now, other properties about bases, they're slippery, or they have a slippery feel. That's another thing you're not supposed to really be doing, right? Acids will react with metals. And I should also point out when acids react with metals, they're generally creating hydrogen gas. So I'm putting a little note down here. There's something called litmus paper that's used to test whether or not solutions are acidic and basic. Let me spell that a little better so you can see it. Litmus turns red in the presence of acid, and then it turns blue in the presence of bases. And litmus is actually a lichen, and so it's the pigment from the lichen that's changing color. And then usually when you get litmus paper that you're testing an acid for, it comes as a blue form, and you put it in the litmus paper and it turns red. And for bases, it's a light red color when you put it in the solution or you detect a base, it ends up turning blue. The other property that acids and bases have in common with each other is they react with each other. So I'm just going to put react with each other. In the middle like that, in a neutralization reaction. And we talked about neutralization in acid-base reactions before, but it's called a neutralization reaction. All right, so those are the general properties of acids and bases that we've covered before. But the other thing I also wanted to point out, and we'll talk a little bit about this later, acids and bases are both types of electrolytes. So I'm going to put that on the middle column too. And even though one is acidic and one is basic, they both give solutions the property to conduct electricity. There's a couple of different definitions of acids and bases that we've discussed before, and one is new for this chapter, and it's the one we'll primarily use from here on out. But the Arrhenius definition is essentially the definition we used before. If you have an acid, it's really defined by its formula as hydrogen in it, and an anion, and when you put it in water, it produces hydrogen ion. Plus chloride like that, so H plus and Cl minus, and these would all be aqueous. And then bases, if you put them in water, for example NaOH, aqueous, you're going to get Na plus OH minus. And both of these will be aqueous. And remember my little shorthand thing when we did the chemical reactions, just put a squiggly line under it. They produce hydroxide. And in the Arrhenius definition, really the definition is based on the formula of a compound. It has hydrogen ion, and it can produce hydrogen ion in solution, or it has hydroxide ion. And remember, for bases, it's a metal hydroxide. That's what bases are, and when they dissolve in water, they produce hydroxide ion. Now, a broader definition of acids and bases is called the Bronsted-Lowry Theory, and this is a proton transfer reaction. So I'll show you what those are, but in just definitions, a Bronsted-Lowry acid is a proton donor. And if it accepts the proton, that's what we call the base. So this is a proton acceptor. So then you might be asking yourself, what the heck does it mean to be a proton, right? So think about hydrogen atoms. So if I have a hydrogen atom, it has one proton, and then it has one electron. So if I take and I make H+, that means I have to lose that electron to make it a positive charge. And really, hydrogen ion is considered in the terminology to be a proton. So this is hydrogen ion is what we refer to as a proton, because that's what you have left after the hydrogen atom loses the electron. So let's I'll give you examples of a reaction, and then this is kind of spaced out funny, unfortunately. But let's say you have HCl, and let's do C. We'll do something that's different. Yeah, we'll do this. We'll do HCO3 minus, like that. Okay, and then after this reaction takes place, I have H2CO3 plus Cl minus, like that. Okay. Now, what's the proton donor and what's the proton acceptor? So the way you can tell is just looking at the formulas. You'll notice how this has one hydrogen and here it has two. So it accepted a proton. So this is the base. And then HCl, since it went from HCl to Cl minus like this, right? This is the acid. So proton donor and proton acceptor, right, are functional, and actually what's happening is we're talking about hydrogen atoms moving from one substance to another, and that's how we're defining acids and bases. So I'll give you another example, because NH3, ammonia, is considered a base. And when I react it with water, this is an equilibrium reaction. Remember, we covered that in chapter 15. You're going to get NH3, 4 plus, and H3, OH minus, sorry, an OH minus, like this. Okay, so now we're going to do this. We're going to ask the question, which was the proton acceptor and which was the proton donor? And I'm going to take a pause here, pause it, and go ahead and predict, and then restart the video. Okay, so NH3 was the base, and you can tell that because it became NH4 plus. And remember, water as an acid donated a proton, and the proton has a positive charge, and so the positive charge went to the NH3 and gave me NH4 plus. That's because of the proton donation. H2O donated the proton to give it to NH3, and as a result, it made OH minus. Now, because this is an equilibrium reaction, we have both a forward reaction and a reverse reaction. So we have a reaction going to the right, and we have a reaction going to the left. We have two things going on. And if you remember, when we talked about being at equilibrium, eventually you get to equilibrium when those two rates are the same. So we can define acids and bases on the right-hand side for the return reaction going to the left. So if you're looking at NH4, right, you'll look at NH4 plus here, and when it goes in this direction, right, it loses a proton. Now, it would be too confusing just to call it an acid, because it is the proton donor on the right-hand side. It is an acid, or it's acting as an acid, so what we do is we call it the conjugate acid, to not confuse it with what's on the left-hand side. All it really is saying is on the return reaction, it's acting as the acid and giving the proton back to the water where it got it from. Okay, or giving it back to the hydroxide to make water. That's where it got it from originally. Okay, so now that's the conjugate acid. So it's not confused. Conjugate, the word conjugate, so it's not confused what's on the reactant side. And then OH minus, if you look at here, right? This is gaining a proton here, or sorry, losing a proton here. So oh, that's just weird. Loss. I'm right. Loss of H plus, right? And then this is going this way. It's gaining H plus. So this is the proton acceptor. So we call it the conjugate base. Now, this Bronsted-Lowry definition opens up a whole bunch of different possibilities for what acids and bases are. And there's some compounds which we can call what are termed as amphiprotic or amphoteric compounds. So take a look at this reaction. I'm going to take H2O, and I'm going to put it with say HF. Okay. This is also an equilibrium, so I get H3O plus F minus, like this. Okay. Now, H2O, okay, accepted the proton, so this is the base. Oh, I'm writing all this in red. That's all right. And this is the acid. And I have a conjugate. Now, maybe you figured this out already. If it's the base on one side, it's the acid on the other side. And you just have to add the word conjugate to it. And fluorine, this is the fluoride is the conjugate base. Okay, so notice something. So notice something funny about H2O. Here, it's acting as a base, and here, it's acting as an acid. So when water is placed in equilibrium with the base, NH3 is considered to be a base, it becomes the acid, and then when it's put in equilibrium with an acid, it becomes the base. So it's kind of like the medium in solution, in aqueous solutions, for carrying around hydrogen ions and doing the bidding of the other compound, either being the acid for the base or being the base for the acid. This is what we mean by amphoteric. It can act as either an acid or a base. Common types of compounds that you see as amphoteric are part of what we call polyprotic acids. So if I have HSO4 minus, it can accept a proton and become H2SO4, or it could donate a proton and become SO4 2 minus. And what it does really depends on if it's being mixed with something that's more acidic than it or more basic than it, and then it can act as an acid or it can act as a base. So let's take a few moments, and on this page, we'll do the first one, or I'll do the first one, and then you'll do the next two. We'll find the acid, the base, the conjugate acid, and the conjugate base. So again, a little more complicated formulas. This is phosphoric acid, right? And it does what, right? It loses a hydrogen, an H plus, because that's why this has a negative charge over here. It lost the H plus. So this must be the acid, and that means the water, right, picked up that proton. So this is the base. So the acid, I should maybe do them in different colors. This is its conjugate base, and the base, this is his conjugate acid, like that. So do the others in the same way, and when I come back, well, I'll pause for a little bit. When you restart, I'll have the answers on the equations for you. So that's what those should look like. So hopefully you didn't have trouble, and if you did, go ahead and send me a message and we can take care of that. All right. A couple other things. A neutralization reaction takes place between an acid and a base. So I'll give you an example of a neutralization reaction. We'll do HCl plus NaOH. And this is HCl is a strong acid. That's one of those things you have to have memorized. Okay. The product. Now, how do you do the product? The same way that you did before. You say H plus and Cl minus. That's what this gives me, right, as ions. And then this gives me Na plus plus OH minus. And these ones can all be gotten from the periodic table. Hydrogen's usually +1, chloride's usually -1, sodium's usually +1. And then hydroxide is actually O2 minus plus H plus. So that gives us OH minus like that. So when you do that, then you do the insides and outsides, and you make new compounds, always writing the cation first. So NaCl would be this, right? That would what you would get from these guys. And the other one would be HOH, but that would actually be what, right? H2O. Now, just a little side here. When you have an acid and a base, these are Arrhenius acids and Arrhenius base because by formula I have the H plus on here. Then what happens is you get a salt and water. This ionic compound of an acid-base reaction is what we call a salt. That's the sort of technical term for it. It's also called salt. This one, sodium chloride, is actually table salt, and water is in the liquid state. So these other ones will be aqueous. I didn't write those in. I don't usually write them, but I just thought it'd be helpful. Now, HCl is what's known as a monoprotic acid, and it's called a monoprotic acid because it only has one hydrogen. So that's what monoprotic means. Okay, so a polyprotic acid would be anything with more than one hydrogen. So you can have H2SO4, and if I react that with sodium hydroxide, you can have actually two different kinds of neutralizations reactions. Typically in a titration, you're only titrating one, but not always. But anyways, so what you get is, and in this case you actually titrate off both, but you could titrate off one or react one, and you'd have HSO4 minus plus NaHSO4 minus. And H2O. Now, how did I get NaHSO4, right? Well, if it only reacts with 1 mole of sodium hydroxide, then what I'd write is I write this. H2SO4 is H plus HSO4 minus. And sodium hydroxide is still Na plus OH minus. So these would get together and these would get together, and that's where I get the formulas from. But typically for sulfuric acid, we're doing what's called a complete neutralization reaction. And in a complete neutralization reaction, you react off both hydrogens. And so you have to be a little smart about this. You have to think, well, that's H plus and H plus, right? And SO4 2 minus. And then you have on the other, and NaOH. Like that. Now, when you think about this in a complete neutralization reaction, your reaction is going to look like this at the end. You're going to have H2SO4, you'll have NaOH, and then you're going to have still Na2SO4, and then you'll have H2O. Now, the H2O comes from this and this, right? But what about this? And it turns out when you balance this reaction, you're going to need 2 of these because of the sodium sulfate. You'll need 2 sodiums. Both in a complete neutralization reaction, both of these hydrogens need to react with OH minus. So we have like partial neutralization. of sulfuric acid, and this is the complete neutralization of sulfuric acid. Typically, when they're asking you to write an acid-base reaction, this is the kind of reaction that you'll need to write. So you'll take care of the two hydrogens by balancing. Okay, so if it was H3PO4, then it would take 3 NaOHs because there's 3 hydrogens, and then you would get Na3PO4 plus 3H2O like that. Okay, so that's how these things will end up being balanced. So keep that in mind. When you see the subscript down here, assume that you're going to need the same equivalent amount of sodium hydroxide to balance with it. So let's really quickly talk about reactions of acids with metals. This is called a single replacement reaction. And in general, you have a metal. So for example, aluminum. And then you have an acid like HCl, like that. And when you react these, you're going to get aluminum 3 plus AlCl3 plus H2, like that. So how did I get that, right? So aluminum makes the aluminum 3 plus ion. That's one thing that I need to know. And so when you balance this formula, what's happening in the single replacement is the aluminum is replacing the hydrogen in the HCl. Now, when you do that, you get aluminum 3 plus ion. That's the ion that aluminum always makes. And then chlorine from the HCl is always -1, so that's how I get this formula over here. Hydrogen gas is usually the other product in these reactions. Now, there's such a thing as the activity series, which we can use to predict whether or not these reactions take place. Now, this is actually something, I think, out of chapter 16 or 17. It's actually a chapter we're only going to partially cover. Okay, so, sorry. Let's look at a couple of other examples, right? So we're going to do magnesium. Let's do magnesium plus HCl. And then what I want you to do is predict what the product of the reaction is, and then predict whether or not it will happen. Okay, so again, what you're going to do is you're going to write this as its ion. So we know that the magnesium is going to become magnesium 2 plus in the product. And it'll have to combine with chloride. And then, excuse me, you'll also have hydrogen gas. This is the definition, basically, of a single replacement reaction of a metal in an acid. Okay, so then what you're going to do is you'll write this. You'll write Mg, and then plus HCl makes MgCl2 plus H2 gas. And then what you end up doing is balancing it, and you end up needing 2 hydrogens here to make it balance. Now, whether or not it reacts, okay, the metal has to be above the acid, above hydrogen, okay, the acid in the activity series. And so when you look at magnesium, there's magnesium, it's above hydrogen. That means it's more reactive than hydrogen is, and will give hydrogen the electron. So go ahead and try copper and zinc, and I'll do them one at a time. I'll come back and do the copper, and we'll do a prediction, and then we'll come back and do the zinc, and we'll do a prediction. So go ahead and try to predict what the products for the single replacement of copper with hydrochloric acid will be. Now, I do want to point out that copper could make copper 2 plus or copper 1 plus, and we're going to assume that it makes copper 2. This is going to be copper plus HCl. And go ahead and pause and try to write it out. Okay, so here it is. Oh, I forgot to balance that. And now we have to look to see where copper is relative to hydrogen, and copper is below hydrogen, and so there's no reaction. So that's why I wrote no reaction. Sometimes we'll write just NR like that. All right, go ahead and do the next one. Okay, so we have zinc and HCl, and so I'll get ZnCl2, so that means I need a balancing coefficient over here. And then I'll have hydrogen gas as the product. Now we have to look at zinc, the metal, not looking at this side, right? We're looking at the reactant side to predict whether a reaction takes place. Zinc is above hydrogen, and so a reaction takes place. It means it's more reactive than hydrogen and will donate hydrogen an electron, and so in this case a reaction takes place. We should also review the gas-forming reactions that acids participate in, and this comes again out of our reactions chapter. If you form any of these products, H2CO3, H2SO3, and NH4OH, you'll form a gas. And the last one is a gas, that's H2S. And so if you form as a product, right, then it decomposes to CO2 and water. And CO2 is a gas, okay, or SO2, and water. And then this will also, NH4OH, ammonium hydroxide, will also give us water. And so that'll be NH3, which is a gas, plus water. The last one doesn't give us water because this is just actually a gas like this. So these are the common gas forming reactions. So just to give you an example, let's take let's do NH4. Let's do NH4Cl plus NaOH, and then again it's a double replacement reaction. So I have ammonium ion, which is NH4 plus Cl minus, and then NaOH would be Na plus OH minus, like this. And then the Na and the Cl will go together, and then the NH4 and the OH go together, and that gives us this NaCl plus, and then NH4OH, and then you should recognize at this point this gets replaced by NH3 and H2O. And this is the gas, like that, okay? So again, gas forming reactions, a little bit of review from earlier chapters. You need to know that if these are formed as products, these ones here are formed as products, these are the gases that are formed, and then if at any time you form H2S, that will be listed as a gas as well in the products. Okay, so this next section, normally I do a titration for you in class, and I show you like how this is done, and it's really awkward not to have equipment. So what I'm going to try to do is skip this page, and then I'll have a little video on it for you next time. There's a lot of terminology, and I'll come back and in the video I'll talk about these things in the lecture. Actually not next week, it's this week now. I'll try to get into the lab and do a little bit of recording about the different pieces of equipment that we use, and talk a little bit about indicators. But really what acid base titration is, it's stoichiometry problems where the volumes are determined um, experimentally. Okay, so what we're going to do is you're going to do a reaction, and that reaction is going to give you information about moles of material, and the volume is going to be important. The volume of solution that's used and the molarity of the solutions that are used are usually going to be important aspects in doing the problems. The volumes in these problems are usually what are determined experimentally. So let me just sort of talk you through the process, and I'm going to try doing some problems here just so you know how to do them for the homework. You can read a little bit about the technique in the textbook, but really it helps to have some video of somebody showing you these things. So I'll try to be doing that in the next day or so and getting that over to you on Canvas. And I may incorporate it at the end of this lecture in the future when you watch it. Maybe I'll have updated it by then, but right for now I'm going to just skip some of this top page and I'll come back to it if I do that. Okay, so in a titration problem, what you want to do is you also want to start the problem with any data that you can calculate moles from. And typically in these problems it's a mass or it's a molarity and a volume. If you remember, molarity is moles per liter, and volume would be in liters or milliliters, and so you can multiply those and you can get moles. And mass, you can use molar mass, and you can get to moles that way. So once you have the moles, then typically you're going to be looking for a quantity. So you're going to use a chemical reaction, usually an acid-base reaction, but not always, to determine the moles of what you're looking for. So it's a stoichiometry problem and a chemical reaction problem. Oftentimes the reactions are given to you for acid-base, or they're assumed. But sometimes for things that are not acid-base, you'll have to write the chemical reactions. And then finally, once you have the moles of what you're looking for, there's a lot of other quantities that you can calculate. You can calculate molarity. You can calculate molar mass if you do the mass of a sample, for example, of an unknown, and you didn't have the molar mass. You could calculate the molar mass if you had the mass and the moles of the substance. So there's a lot of very different variations, and so what I'm going to do is show you a couple of those now. And we'll just follow this same format. It says, if 32 milliliters of 0.15 molar NaOH is required to titrate a 25 ml sample of HCl to its endpoint. So that's what that means is this volume gives you the exact number of moles as this volume in molarity. Okay, so these two are related to each other by the chemical reaction. What was the molarity of the HCl solution? So what can you use out of this to calculate molarity? And if you look, right, I have a volume and a molarity of NaOH. So this can be used to calculate moles. So that's what I'm going to write here. I have volume and molarity of NaOH. And molarity, this is the moles per liter, that's a big M, sorry. That's 0.150 moles per liter. Remember, that's the way I told you to write that in the previous chapter. What is the chemical reaction? So then you have NaOH and HCl. So NaOH plus HCl, and this is an acid-base reaction, and so you'll figure out what the ions are, and what you'll come up with is NaCl plus H2O. So that's the balanced reaction. It's the acid-base reaction between these guys here, like that. Okay. And then what are you looking for? And what you're looking for is the molarity of the HCl. So what do you need to know? You need to know the moles of HCl per liter of HCl. So now we can do this problem, okay? So to begin with, I have 32.05. Well, let me write it up here. 32.05 mLs. And I'm going to convert that. Oh, sorry. I'm looking for moles of NaOH. So I have 35.05 milliliters. Now, just before I write the next thing, what people attempted often to do to write this right away, but notice that this is liters and milliliters, so we'll want to convert that over. So it's 1,000, this is how I learned it, right? Milliliters per liter. And then it's 0.15 moles per liter. And so I'm going to do that calculation, and that will give me 0. It's a small number, so don't be surprised when you get these. 0.0052575. Now, sig figs I have 3, so I'm going to just underline that for now, and that's moles. And now I have a chemical reaction, and I'm looking for HCl's, molarity of HCl. So what I'm going to do is this. I'm going to say moles of HCl, because that's what we're going to have to do first. It's 0.00525575 moles of NaOH times, and then it's 1 mole of HCl for every 1 mole of NaOH, like that. So in fact, this number is the same as this number of moles of NaOH is the same as the moles of HCl. So 0.00525575 moles of HCl. Now, to do the molarity, what I need to do first, now notice this is what I needed here, right, for this calculation. It almost always works out this way, but almost always works out that way, that what you're looking for is kind of part of the solution, right? And so you write out what you're looking for. All I need to know then is the volume of HCl, and that's where this comes in. So that's 25 milliliters. Now it's 25.00 mLs, and this needs to be liters, right? So it's 1,000 milliliters in a liter. That becomes 0.02500 liters. And then I'm going to write 0.02500 liters and 0.00525575 moles of HCl, like that. And that'll give me my molarity of HCl. And so you plug that into your calculator, and you'll get, let's see, 0.210 moles per liter, or 0.210 molar, like that. All right? All right, let's see. Let's do another example, and this is time I have grams. And it says a 1 gram sample, 1.00 gram sample of magnesium hydroxide is titrated with 17.89 milliliters of HCl. Calculate the molarity of HCl. So what can you calculate the moles of, right? In this problem, it looks like I have grams, and I don't have a molarity and a volume, because I have a volume and I have a molarity that I'm looking for, but I don't have both, so I can't calculate moles from that. So I can calculate moles from 1.00 grams of MgOH2. So I'm going to calculate moles of MgOH2. That's going to be 1.00 grams of, not GR, G of MgOH2, and then I'm going to convert it with the molar mass. So I need grams at the bottom and moles at the top, and I'll look that up. But it's MgOH2 like this, and if you use the app or look it up, what you're going to end up with is 58.32. Okay, so I'll run that on my calculator, and that gives me 0.017147, and I only have 3 sig figs, so that's to there, moles of MgOH2. So what is the chemical reaction, right? Because I'm trying to go from magnesium hydroxide to HCl, and so the reaction is going to be MgOH2, and then plus HCl, and then when you write the products in balance this equation, you'll have MgCl2 plus 2H2O, and I put a 2 in front of the HCl. So what we're going to be doing is calculating moles of HCl. So moles of HCl, that's going to be 0.017147 moles of MgOH2. And then now the stoichiometry is 2 to 1, so it's 2 moles of HCl for every 1 mole of MgOH2. Okay, so when you do that, that gives you 0.03429 moles of HCl. Sorry. And then finally, what are you looking for? Well, you're looking for the molarity of the HCl. And again, this is moles. So whatever you're asked for, but in this case it's molarity per liter. And so the problem is, again, and this often happens in titration problems because the device that we use for measuring measures in milliliters. It's 17.89 milliliters of HCl. So it's going to be 0.017, oops, sorry, went too far, 89 liters of HCl for every, and the top is going to be 0.03429 moles of HCl. So I just take the answer from the previous and then divide by that volume, and that gives me 1.9. 2 when you round it to 3. Remember, we have 3 sig figs. 2 moles per liter, or 1.92 molar, like that. Okay. So again, these are a little bit tricky. We'll have a worksheet. There'll be some practice problems on there, but there won't be a whole bunch of them. But you need to get used to this pattern of what can I use to calculate moles? What is the relationship, the chemical reaction between what I have and what I'm looking for, and the chemical reaction? So you'll write a reaction to balance. And then specifically, what are you looking for about it? And both these problems, I just realized, are molarity problems. But sometimes you'll be looking for mass. And so if you have the moles of products, you'd multiply by the molar mass, and you would have your answer, for example. So one of the things I wanted to do was talk about hydronium and hydrogen ion. You know, in an acid-base reaction, oftentimes, for example, HCl plus H2O, that makes H3O plus Cl minus. This is hydronium, right? Or we could have written HCl goes to H plus Cl minus. And I didn't talk about this before. I think I had a note in there and I had forgotten. But actually in water, these two things are the same. And it turns out, like, hydrogen ion, and being just a proton, is super unstable. And so what happens with it is water with its electrons like this can connect to it and help stabilize that. And now again, this is just a hydrogen atom, right? And what it does, a hydrogen ion, what it does is it takes on this formula that looks like this. With a positive charge, okay? So this is hydronium. And so when we talk about hydrogen ion H plus or hydronium, we really, in water, we really mean the same thing. So remember, we have something called strong acids. And in strong acids, what you need to remember, that these completely ionize when they're placed in water. So for example, HCl, HClO4 is a strong acid. That's that list you need to memorize. Plus H2O in water forms H3O plus ClO4 minus, like that. So if you have a bottle, and let's say your bottle says, your flask, let's say it's 1 molar concentration. Kind of looks weird. Let me just redraw that. 1 molar concentration. What you end up with is actually 1 molar of hydronium ion, because this completely ionizes, and when it does that, it completely transfers the 1 mole per liter of hydrogen to water to make the hydronium, and then you also have 1 molar ClO minus perchlorate ion. So when we talk about hydronium in strong acids, the molarity of the acid, that's what that should say, is equal to the molarity of the hydronium. Now, for strong bases, we follow the solubility rules. So for strong acids, we follow the list of memorized strong acids. And for strong bases, we follow solubility rules. So if you have sodium, for example, sodium hydroxide is all sodium compounds are soluble, and that it's aqueous as a result, and ionic compounds that are aqueous break into their ions, Na plus OH minus. So if you have a 1 molar sodium hydroxide solution, you actually have a 1 molar solution of hydroxide ions and a 1 molar solution of sodium ions floating around in the same solution. They completely ionize and separate from each other. Now, let's say you have a weak acid, right? So put it in perspective. HCl, which is one of our strong acids, plus H2O, right? If I have a 1 molar solution, then I have 1 molar H3O plus and 1 molar Cl minus. So 0% of it is HCl and 100% of it is hydronium and chloride. Now, when we do weak acids, the definition of a weak acid is an acid that only partially ionizes in solution. So if I have HF, I can write the same reaction, HF plus H2O, right, makes, and this is equilibriums. When they're weak acids, we put equilibrium. H3O plus F minus. Now, for all practical purposes, these two reactions look the same. They're written in balance the same way, okay? But usually 99% of it is still on the reactant side, and only 1% of it is product side. Anywhere from 1 to 5% is on the product side. So what we know about weak acids is that if you have a 1 molar bottle of HF, okay, you have your concentration, your hydronium ion concentration, is much less than 1 molar. Now, remember, ions are what make solutions conductive to electricity, and we have these terms. Again, this is a review: strong and weak electrolytes. The strong electrolytes are the soluble salts, so soluble ionic compounds. And strong acids. And the weak electrolytes are actually the weak acids and weak bases. The most common weak base are things containing nitrogen, like ammonia. Ammonia is a weak base, and when you combine it with water, it forms ammonium ion. This is a reaction I wrote earlier, plus OH minus, like this. Okay, so again, thinking about equilibrium, this is 99% of it roughly is like this, and 1% is like that. So there's very few ions actually in the solution, just like there are for weak acids, and so these make weak electrolytes. For strong electrolytes, it 100% dissociates or ionizes. Those are strong electrolytes. And then we have the classification of non-electrolytes, and these are molecular compounds. Or covalent compounds that aren't acids, because acids are actually ionizable, but most molecular compounds are not. Things like alcohol, ethanol, for example, CH3CH2OH, even though it looks like it's a base because this part is not a metal, it's a molecular or covalent compound. Those are non-electrolytes. Water is a non-electrolyte. And sugar, which I won't draw its structure, but for example, glucose is C6H12O6, because there's no ions that are created by those. Those are all non-electrolytes. Well, there's something called, in the next part, we're going to actually do a lot of calculations, and they depend on the equilibrium of hydronium and hydroxide in water. And there's a reaction, and it's called a self-ionization reaction. There's a lot of substances that do this, but water's is probably the one that's best known. I have H2O plus H2O in a chemical reaction. And what happens is these will act like acids or bases. And so what happens is one of them will be the acid and donate a proton, and one will be a base and accept a proton. So for example, I can have H3O plus, and then I can have OH minus. And this is known as the self-ionization reaction for water. Now this is liquid, pure liquid, and those are not included in equilibrium constants. So I can write the equilibrium constant expression for this as K is equal to the concentration of hydronium times the concentration of hydroxide, like that. And because this is for water, it has a very special subscript just to designate it. That's the equilibrium constant for water. And this is the equilibrium constant expression, and it's actually equal to this number, 1 times 10 to the minus 14. So you can use that if you're given the hydronium ion concentration. You can use that equation to calculate how much hydroxide is in the solution. So for example, I have this problem that says calculate the concentration of hydroxide ion if the concentration of hydronium is 1.59 times 10 to the minus third. So I'm looking for hydroxide ion. So I know Kw is equal to hydronium, H3O plus, times hydroxide, OH minus. And I'm looking for hydroxide, so I'll divide through by H3O plus. And that'll leave me with OH minus by itself. and that's going to be equal to Kw divided by H3O plus, like that. And now I can plug the numbers in. This is 1.00 times 10 to the minus 14. That number never changes, always the same in this class. Okay, now it does actually depend a little bit on temperature, but in this class it's always that same number. And then the concentration of hydronium ion is 1.59 times 10 to the minus third, like that. So we'll do the math. Oh, and this is what I want to make sure you do. Try doing this on your calculator and make sure you can get the right answer. So what I get when I do this calculation is 6.29 times 10 to the minus 12. And the units for these are molarity. Sorry, I meant to mention that. Actually, the kW units are molarity squared because it's a molarity times a molarity. So this unit for concentration comes out in molarity. All right, we'll do practice with that actually. We'll do a worksheet this week, Thursday and Friday actually. I'll have office hours where we'll be working specifically on this worksheet. But we'll do it in the lab period as well this week, and so I'll post that, and so we'll really do a lot of practice on these particular calculations. I just want to give you some examples to work from. Okay, so these kinds of numbers, when you see them, just kind of make your eyes swim. I mean, it's really not, I don't know, helpful really to look at them. And really because of that, what scientists have done is chosen to express these as log functions. And I know probably you haven't dealt with log functions in a long time, or they leave you a little uncomfortable. But we use log expressions to help make a scale for pH, which makes sense numerically to our minds. Okay, so the pH scale goes from essentially 0 to 14. Now, technically, it can actually exceed that scale, but if I make that's a horrible diagram. I'm going to draw a line here, and then I'll draw the ends on it. How's that sound? There we go. That's easier. In the middle of the pH scale, we have pH 7. So this is pH. And pH 7 is considered to be neutral. The bottom of the pH scale is usually given around 0, and the top is 14. So already you can see how these numbers, instead of looking at molarities, are a lot easier to look at. Stomach acid is around pH 2.5 usually. So let's see, so that would be like right around here. So that, oh great, sorry, gotta erase the right line. Get rid of some of these, there we go. Right around here, this is stomach acid. And oddly enough, that's pretty close to where soda is at, like Coca-Cola, but all carbonated beverages consist of carbonic acid, and the pH is usually around 3 or so. Vinegar is around 4, so if you had a 4 here, this is 4, this is 2 to 3, 4 would be vinegar. Neutral, pure water that's been boiled has a pH 7 typically. And then this is considered to be acidic. Above 7 is considered to be alkaline. That's why we get the names alkaline earth metals. If you take sodium, for example, like sodium metal, and put it in water, it actually makes the pH very close to 14, way out at the top. Now, that would be the same as lye, but you're making it chemically from sodium. So the high pH scale is very basic, okay, or alkaline, and the acidic end of the scale is everything below 7, okay? Now, some definitions on how you calculate the pH from molarity. There's pH, is equal to the negative log of the hydronium ion concentration. And a lot of times you'll see people just write that as H+, but really they know usually that it means hydronium. You can also calculate POH, and on this side we'll have POH, and it's 0 at the top and it's 14 at the bottom. So POH is equal to the negative log of the hydroxide ion concentration. And then, if you notice the relationship of the scale, one's 0 when the other's 14, and one's 14 when the other's 0, it turns out that pH plus POH is always equal to 14. And a couple of other relationships that you need to know for this, that's going to be this one, this KW expression, that helps us to convert things in the pHs and the pH scale. A couple of other things that you're probably a little rusty on, but if you wanted to calculate the hydronium ion concentration from the pH, then it would be 10 raised to the negative power of the pH. Okay, so you add a negative sign and then you type in your pH there and raise it to the 10 power. The concentration hydroxide is going to be 10 to the negative power of the OH concentration, of the POH, sorry. And the P of pH and POH, that stands for power, so it's the power of 10. So when you're calculating the pH, you're calculating the log of a number. That's the power of 10 that is going to give you that pH value, that represents that number. So let's try some calculations. We're going to take and calculate the pH of a 0.025 molar HNO3 solution. And so we're going to say pH is equal to negative log of 0.025. And remember, this is a strong acid, so the molarity of hydronium is the same as the concentration of the acid. And again, this is one of those calculations that you really need to make sure you know how to do. And if you're using the calculator that I recommend for class, what you need to do is hit the log button twice. If you hit it once, it gives you natural log, and if you hit it twice, it gives you a base 10 log. That's what we're doing. So this comes out to be 1.602. For sig figs, we'll just keep 2 decimal places, okay? Now we're going to do the POH, right? POH and the molarity of sodium hydroxide, again, negative log, right? And the concentration of the hydroxide ion, and because it's a strong base, the hydroxide ion concentration is the same concentration as the sodium hydroxide, and that'll actually give you the same number, like that. But one's a pH, it's the log scale of the hydronium ion concentration, or the log scale of the hydroxide ion concentrations. Okay, so now we're going to do a couple of more examples, but before we do those examples, and this is actually the last page of these notes because this next part's the nuclear chemistry stuff. But before we do that, I wanted to show you some of the relationships that you can apply in order to do these calculations. So let's say you have POH and you wanted to calculate OH. Then you're going to use that equation, right? If you have the OH and you want to go to POH, then you'll use this equation. So the way I've got this thing set up is if you're going to go up, it's the inside equations. You're going to go down, it's the outside equations. So these are all related to each other. So if I have pH and I wanted the OH concentration, there's 2 ways to go. I can either go this way, or I can actually go backwards this way using these equations to do that, this one and this one. Or I can go in the forward direction and use this equation and that equation. Or this equation, sorry. So I just wanted to make sure you're aware that I put this chart here to show you what you can calculate from what. So for example, I have to calculate the pH of a solution with a pOH of 6.5. Well, using this chart, right, that's this and this, so the equation that I'll use is that. So, to do the calculation, I have pH, let's see, plus pOH is 14. And now I want the pH, right? So that means pH is equal to 14 minus pOH. I rearrange that equation, so I have 14, that's 0.00, minus 6.5, that becomes 7.5. So that would be the pH of that solution. Okay, let's do another example. I'm going to erase what I did on here. Calculate the hydronium ion concentration, right, of a solution with a pOH of 2.8. Now, I'm looking for hydronium ion concentration, and I want to calculate the pOH. Now, I will tell you that you can go either of two ways, but what most people choose to do is if they can use this relationship, that's the relationship they'll use, because it's mathematically much easier to do, and there's usually fewer errors. So if you can incorporate that into your pathway, it's going to help guarantee you make less mistakes. So here's the deal. In order to get the hydronium ion concentration, I have to also calculate the pH in this problem, and then I'm going to use this equation here to calculate my hydronium ion concentration. So it's a two-step problem. The diagram's telling you that by identifying the two things that you're trying to find, or what you're trying to find from what you're given. Okay, so I'll do this. We'll write it out. So I have a pOH at 2.8, so that means my pH is 14.00 minus 2.8. Okay, so that's going to be 11.2. And I didn't give any sig figs on that, so that's what that is. And then to calculate the hydronium ion concentration, the concentration of hydronium, H3O+, that's going to be 10 raised to the negative power of, and then I have to plug in my number, 11.2. Now, again, this is a calculation that is a point where people will tend to make a lot of errors, and so I would recommend strongly to you that you practice this. You're going to do a worksheet this week. I'll post that tomorrow or tonight. And you need to make sure you can do it, because for sure you're going to get questions that are very similar to this where you have to do a calculation. So you get 6.3 times 10 to the minus 12. So it's a very low concentration, but that's the equation or the pathway you'll follow. And we'll do one more, and this is what I'd like you to do. I'd like you to identify what you're given and then decide how you're going to do the calculation, okay? So I'm going to erase this again. So find the given and what you're looking for and decide which way you're going to do the calculation. So I'm going to pause it, and then I'll go through the calculation with you, but you could also just go ahead and do it and then watch me while I do it. Okay, so I started doing it, and then we'll be able to do the calculation pretty quickly from here. In order to do this calculation, what you have to recognize is that, look, it says if this is that, so I have the OH value, and I'm looking for the pH, and like I said, if people can incorporate this equation, that's typically the way they'll do it. So, how do I do it, right? I take the negative log of my hydroxide ion concentration, and that'll give me my pOH. So, negative log of 2.35 times 10 to the negative third okay, there we go, and I get, oh, hang on, I put in I didn't put a decimal. That becomes 2.6289. 3 sig figs, so we'll go for there. Actually, 3 sig figs, I'll just tell you, is actually here on a log number, and that takes a long explanation, but don't worry about sig figs on these. Just be close. And then what we'll need to do is we'll need to say pH is equal to 14 minus pOH. And that becomes 11.371. So there's the pH of a solution whose hydroxide ion concentration is 2.35 times 10 to the minus third. Okay, so the last thing I want to do is talk a little bit about buffer solutions. And a buffer solution is always made out of two specific components. And it's an acid on one side in a reaction. We have water usually on the other side. And then its conjugate base over here plus hydronium. These are the components that we always have in an acid. So this is a weak acid, though, to be very specific. So for example, an example of a very important buffer in our bodies is the carbonate bicarbonate buffer system. So HCO3 minus plus H2O makes CO2 minus CO3 2 minus plus H3O plus. So this is a weak acid. Now it's the conjugate. Actually, it's comes from H2CO3, and H2CO3 is a weak acid. Turns out HCO3 is also a weak acid, and this is the acid Bronsted-Lowry definition. It's the proton donor. This is the proton acceptor. So this is the acid in its conjugate base, but this is weak. Okay. And these two are in equilibrium with each other. There's another one. It's the carbonic acid one. I'll go ahead and write that one too. This is the first reaction I didn't write. H2CO3 plus H2O makes HCO3 minus plus H3O plus. Okay, so let me explain to you why this system is important. Okay, so these are all equilibrium reactions. So buffer systems are weak acids in equilibrium with their conjugate bases. So let's say you are working out really hard, and one of the things that will happen is your body will produce hydrogen ion. And so hydrogen ion is actually in the form of hydronium. That's this, right? And because this is an equilibrium, you could think of Le Chatelier's principle. Le Chatelier's principle says if you add the product, the reaction at equilibrium will shift to the left. So if your body overproduces acid and goes into what's called acidosis, then what will happen is you can have a lot of like bad things, tissue breaking down and stuff as a result of that. But very simply what your body does is converts this into carbonic acid, which then decomposes. This is a gas-forming reaction to CO2 and water. So it's a way for your body to eliminate excess acid, and also every once in a while your body will generate excess base. And when you have excess base, what happens is it removes the hydronium, right? And then your body can produce more hydronium so you don't become too alkaline in your system. But typically, what we call acidosis or acidic conditions occur more frequently than basic conditions. So buffer systems are a way for your body to control the pH. And by definition, this is the definition of a buffer. Buffers, okay, are solutions, And the solutions in particular that have these acid-base equilibria going on are solutions that resist a change in pH. And so your body has a pH right around 7 to 7.4, and the way your body regulates that pH is by either consuming extra hydronium so you don't become more acidic, or by producing some hydronium so you don't become too basic. And it's all from this equilibrium with carbonate and bicarbonate. Well, that's it for the acid-base chapter, and we'll continue on in the next lecture with our last chapter. Actually, it'll be this chapter 17 on nuclear chemistry. If you have any questions, feel free to send me a message.